Hello and welcome. Today we're going to talk about logistic population growth. So logistic population growth is an extension or a refinement on exponential growth. So first let's talk about exponential growth. We know that exponential growth, that we have some population, and that population it's dp dt, the rate of change of the population is somehow proportional to the amount that's there. So we say it has some k of p. Okay, and we think of this as being a positive. We know the solutions of this are p of t is equal to p naught, the initial population, e to the k t. All right, and of course you're going to get graphs that look something like this. And they go up forever. They go on to infinity as time goes forward. Okay, and it starts at p naught right there. Okay, and of course this is unrealistic. Okay, we can't really have exponential growth, at least not for every time. It may start out, maybe it's realistic for a little while, but eventually it goes up. And of course it's unrealistic because you can think of a few examples. We're going to run out of food. The population will somehow be limited by could be food or other resources. It could be habitat. It could be that there are waste products. You can imagine lots of different scenarios. So for instance, if you had bacteria in a petri dish, they might start off exponentially growing. But after a while, all the yeast or bacteria in the petri dish, of course, are going to start pushing out waste products as they're growing, and that could inhibit further growth. All right, so what's really happening here is that if you have a scenario where this is a scenario where when population is small, there is sort of quasi-exponential growth. It seems like it's exponential, but as the population gets bigger, as it increases, then dp dt, the growth rate, starts slowing down. Okay, so we need some sort of equation that expresses this fact, this natural fact that populations are self-limiting. So this self-limiting means that it's not just that something outside of the environment came in and destroyed all the population, but rather the reason the population slowed down is because there were more individuals. And this is the idea that there's a limited resource of food, and because there's already a large population of bacteria eating that food, more bacteria can't find more food to eat. Or the habitat gets smaller, there's just not enough room, and that's because there are other individuals already there. So that's what they mean by self-limiting. Or environmental waste, like all animals have waste products that can poison and poison future generations and therefore limit growth. So the idea of self-limiting, that should be critical in the model. So what we want actually is that we want a dp dt equals to k p, but we want to somehow modify this equation. What we're going to do, of course, is actually say that the growth rate, so this is that growth rate, what we're going to do is now make it a function of the population. Okay, and that's a perfect way to express self-limiting. What we want, of course, is the following, that that k for p is large, or relatively large for small p, and that at some point, at a certain critical value, at p equals L, some critical value, that k of L is equal to 0. We'll call that 1 at 2. And then 3, when p is bigger than L, then k of p is actually negative. So large, and I should say positive. Okay. So what kind of thing can do this? Well, the simple, and many equations could fit this scheme there, but the simplest is have kp be equal to L minus p. All right. So that could be our function for growth. We can actually times it, multiply it by some constant of proportionality, which I'll call kappa, and just to contrast it with k, but it doesn't really matter. So let's look on the next page and see if we can elaborate on this issue. All right, so we're going to have now is we have dp dt is equal to k of p times p. That's our new growth equation. But now, of course, we have this self-limiting growth rate. Okay, and let's look at this growth rate. We can actually plot it just to get an idea of a better sense of this stuff. Okay, so of course, so for here's p on this axis here. What we have is p is on this axis down here, and when p is 0, of course, our population, it's just going to, the rate is going to be kappa times L. Let's write that in. So this is actually kappa times L minus p times p. All right, and so for this, k of p is going to be kappa times L minus p, and this is simply a linear equation, and it's going to go down, and at p equals L, it's going to go negative. All right, so here we have a growth. There's more growth, than death. And down here, of course, anything that's a negative growth rate, this right here, is of course death. Okay, so what that means is that there are more deaths than births in that kind of situation because you've exceeded the limit of population. So the L then, it could represents basically the capacity, or limiting population for the environment or the particular system we're in. It's some sort of limiting population. Okay, so let's now study this more qualitatively. Let's actually draw a slope field. Okay, so let's do that. So again, I put P is on this axis, and then we're going to put T on that axis. Okay, and we already know this equation has 2 points where the slopes are 0, and that's of course P equals 0. We see the slopes will all be 0 like that. Okay, and then at P equals L, up here at L, the slopes are also going to be 0, like so. Okay, And then between, actually at L over 2, halfway between, if you can actually look at this equation and realize very quickly that the slopes are going to be the largest positive values that can be achieved, right? And then everything nearby it, above and below, will be slightly less of a slope, still positive. And then if you get closer and closer to these zero slopes, of course, the slopes start to slacken a bit. I should make sure to draw that so that they are actually less. So like that. Now if you go above L, of course, right here, you get into death. And so the slopes are now negative like this. And they get bigger and bigger negative values as you increase above there. All right, so clearly this shows a lot about the behavior of the system. There has to be some equilibrium population there. So obviously there'll also be an equilibrium at 0. And if you start at some P naught, this is your initial condition, you can see that if I just follow these slope lines, it's going to go up like this. So I'll just kind of fill that in so it's clear what it looks like. And that curve, it actually has a name. It's called a sigmoidal, or a sigmoidal shaped curve. Many curves have a sigmoidal shape, but it's any curve that has this sort of shape. Okay. And of course, if you have a population bigger, you see you get just decay. If you get a population bigger than that limiting population or that capacity for the environment, then you'll decay down. That's called a sigmoidal curve. And the model that we're dealing with here, dp dt times kappa p L minus p, is called the logistic dE. And the growth, P of t, has a behavior that they call logistic growth. And it's very critical and is used in many applications to describe the behavior of systems that have a self-limiting property, that they're self-limiting. Okay, so now that we have the basic qualitative features shown, and we have an idea also of what the solution is going to be looking like. All of those, let's put it together. Now let's actually go through and solve the differential equation. All right, so let's write down our differential equation. dp dt is equal to kappa times p times L minus p. What we have here is that kappa and L, we'll say, are both positive numbers. Okay. We also have an initial population size, which we'll call P naught. Okay, so there's our initial value problem, and we're going to solve this for a general population, initial population, and oops, I always do this. This is always something that happens with if I touch my drawing pad just the wrong way. Sorry about that, guys. All right, let's get back to business. All right, so this is actually solved via separation of variables. Okay, so clearly the kappa, that can stay over on the t side, and this whole thing, this whole expression actually gets divided over. So we have dp over p times L minus p is equal to kappa dt, integrate, integrate. So we're going to integrate the right-hand side. It's easy. It's just kappa times t plus c. And now over here, this we're going to have to use, this might be unfamiliar to people, but we'll have to remember it from our calculus days. This is actually, we're going to have to use partial fractions. Okay, so partial fractions, we're going to use partial fractions on this. Okay, so let's recall what that is. What it says then is if I have a rational expression that's factored into two binomial factors like that in the denominator, then I can express this, I can break up the two factors into two smaller or simpler rational expressions involving those same binomials. Okay, so there we go. And this is true for some a and b. We just have to find it. So of course we multiply everything by p minus l. And this a and b, once we find it, it's true for every p value we pick. And so we do this. We multiply both sides by p times p minus l. Oops. L minus p. I made a mistake. L minus p. L minus p. Sorry about that. Okay, made a little transposition error there. It happens. That's L. A times L minus p plus b times p. All right, so I said this is true for every value of p, so it has to be true for a very particular value of p. So I'm going to actually try, first I'm going to try p equals 0, and then I can conclude then, if I try that particular value, I get a times L is equal to 1, and therefore a has to be equal to 1 over L. If you try p equals L, that's the other case I can look at, it turns this term, it makes it go away to 0. And then we get the following, 1 equals b times L, which of course implies that b is also 1 over L. Perfect. All right, so we get here, there it goes again. Sorry about that. It's just one of the risks of using this drawing pad. What we have here is then the integral. This integral here then can expand out. I can put the 1 over L outside, 1 over P, plus 1 over L minus P dP. And that's, of course, all equal to kappa times T plus C. So I see that L over there, and I'm actually going to multiply everything by L. I'll put that L over there and just leave it there for the duration. Okay, so of course the L multiplies to the C. The C is that undetermined constant, and it simply absorbs the constant. All right, so this part right here, that becomes natural log of the absolute value of P. And this one here, oops, becomes minus natural log of the absolute value of L minus P. Okay, good. All right, so, and then on this side we have L times kappa T plus C. All right, so we have these absolute values. We need to actually consider this case by case. So first of all, P is a population. So we're always going to assume that it's greater than 0. It's uninteresting to assume another case. So absolute value of P is equal to P. But here we see that if L, the absolute values will depend critically on whether or not L is smaller than P or bigger than P. And so what we're going to actually do is, let's assume for now, let's assume that P is less than L. That we're talking about the case that's the population is below its carrying capacity or its limiting value. So in that case, of course, we can remove the absolute value of L minus P is equal to L minus P. Okay. So then I can remove those absolute values. But the other thing I can do is also see that the difference of logs is the log of the ratio. So I can go L, the natural log of P over L minus P. And that just takes this line here and rolls it all up into one natural log. All right, and then we have that L times kappa T plus C. All right, and then of course I exponentiate both sides. And then we get P over L minus P is equal to E, whoops, A, that's our constant, E to the L kappa T. Okay, so now we have to actually solve for P here. And so that will take a few algebraic steps, but just bear with me. We have to multiply everything by L minus P. Yeah, we'll just do that. So that's L kappa T. And then we have to distribute through and collect all the P, anything involving P, and bring it over to one side. So we have a P plus A times P e to the L kappa T is equal to L A e to the L kappa t. All right, so we're going to factor out the p there and divide. So we're going to get p of t is then equal to L A e to the L kappa t all over 1 plus A e to the L kappa t. So at this stage, I'd like to, I'm going to actually multiply everything. I'm just simplifying at this case, in this case, or at this juncture. I'm just kind of simplifying the equation to make it a little easier, a little bit more palatable to look at. And then what we get here is we get an LA all over A plus e to the negative L kappa t. All right, so that's looking a little bit simpler. The question then, of course, is what is the value of A? Well, it might be easier to look at the A over here. I'm going to look at this one. So if I actually put t equals 0 there, then we know that the P is equal to P naught, right? So what we get here is P naught over L minus P naught is equal to A. Okay, so that can help us a bit. So again, here's our P of t. Now we're going to have to go to a new page. I'm going to write these down on the new page, and then we're going to simplify it as best we can to get to our final answer. All right, let's do that. So what we have here is P of t is equal to L A over A plus e to the negative L kappa t. And then we had there that P naught minus L minus P naught was equal to A. So let's just do a little bit more simplification and finally get this thing in form. Now what we can see here is this will cancel with that, but we have to multiply it through, and then we're going to get an L P naught all over P naught plus L minus P naught times e to the negative L kappa t. All right, and that will be, I think, our best, most simplified expression for this equation. So this often is called a logistic equation. A lot of people put it in maybe a slightly simpler form. You know, it's just going to be something A B plus C e to the negative, I'll just put alpha t. That's the most general, generic form of the logistic equation, but here's a nice way of understanding it in terms of a population type model. And of course we can graph it as follows. It's going to be this sort of sigmoidal, as they say, shaped curve that limits at L. So let's just check to make sure this thing works. If I put P equals 0 in here, I'm going to get an L over P naught, L times P naught over P naught plus L minus P naught, right? And clearly you can see that simplifies to P naught. And then the other one we want to look at is actually when t goes to infinity. We want to see that does it actually go up to here and limit. And in fact it does. You can see this, L minus P naught all over P naught. And then of course this term right there, that just goes completely to 0. So we go plus 0 and that becomes L. Okay, so that definitely works. All right. And then the other question is, what happens then for P naught that's actually bigger than L? And it turns out that this formula works for both cases. It works for P naught bigger than L, and also the case that we originally consumed is less than L. It works for both. And so it just turns out that this equation it works for both. That the analysis we did of cases, it all works out in the end that it's the same equation. So in fact, in that case, what you'll see is exponential decline type behavior like that, and it also limits to L. whether you go above or below L. Okay, so I hope that gives you an understanding, a clear understanding of how sigmoidal or logistic growth works. But there's always a point in the logistic curve, I think that's to note, where you have that maximum growth. All right, and it's always going to be at L over 2, and that's really critical. So although your growth rate is higher, K of P is big as population is low, because you don't have a very big population, growth isn't as big. And then you get to the sweet spot right in the middle of your population. The population's big enough that you get good growth, and you're not limited yet too much by the downsides of population growth. And then you get the biggest growth in population, the biggest rate of change in the population. But as you grow any higher, there is that self-limiting behavior as you get closer and closer to L. So I hope that now clarifies, and we've learned a whole bunch of new things about logistic equation and logistic growth, and also a bunch of, I would say, more higher level methods of solving differential equations, and quite a bit of significant algebra we did here to get this thing going. So a lot of skills at play here. Thank you very much.